A very good morning to the panels, Muhammad Faisal bin Zulkifli and Zulkifli bin Sharif. The title of my project is Design and Development of Bowtie Antenna for Energy Harvesting. My name is Yogasheni from 4BETS1/2. My supervisor name is Nurul Halim bin Hasim and my co-supervisor name is Dr. Muhammad Inam Abbasi. This is my poster presentation. First, let me show regarding the introduction. As we know, most of the electronic devices, for an example, our smartphone, uses batteries, and due to these batteries, there are issues such as the device size increases, or also there are more needed of maintenance due to battery lifetime. This is why I have designed a bowtie antenna for energy harvesting where it supplies the power. Next is the problem statement. What are the problems in this project before I start the project? So there are two problems which are actually the disadvantage of the bowtie antenna, because number one, bowtie antenna has a poor transmission efficiency, especially during lower end of frequency range. But this can be solved by adding in slots or transmission line, or you can even do it ultra wideband antenna as well. Second problem is the two-dimensional biconical antenna causes limitation in RF signal detection. Maybe you can add more antennas, make it wider. There are more kind of solution towards the problem statement. There are three objectives in this project, which means these are the objectives that need to be achieved in this project. Okay, number one, to design and simulate a bowtie antenna with a frequency range from 500 MHz to 3 GHz for energy harvesting. Number two, bowtie antenna work in a 360-degree pattern and both directions. Number three, to fabricate the bowtie antenna on PCB board. Now, let me explain regarding methodology. Methodology is the methods that has been done in this project to complete the project. So first, step one is the design of slotted bowtie antenna in CST software. The first image is to show how is the CST software looks. Second is the front view of the antenna on top of the substrate. And the third image is actually the back view of the antenna. And this CST software I will show in the next presentation regarding simulation. And then step two is the fabrication of slotted bowtie antenna on PCB board. As we can see, the first one is the fabrication at fabrication lab in FTK. And then next is actually at FKEKK, where, as you can see, I am fixing on the antenna on the receiver signal. It's in the RF chamber actually. So that the antenna actually acts as the receiver signal. And actually opposite of it has another antenna which is a transmitter that transmits the signal. And the reading will be recorded in the UTAM far field measurement system. The result and the analysis. Okay, I have do a comparison here between the performance parameter of simulation and also measurement. This measurement is actually the result from network spectrum analyzer. First, let's compare the frequency. In simulation, as you can see, the frequency is 1.1151 GHz. In measurement, it is 1.215 GHz and also 2.25 GHz. There are actually 4 operating frequencies, but why I choose these two, this is because the next, VSWR. The VSWR must be always between 1 to 2. That shows that it's a competent antenna. As we can see in simulation, the VSWR is 1.23. In measurement is 1.34 and also 1.75. Why I didn't choose the other 2 operating frequencies? This is because their return loss are only at -5 and also their VSWR is more than 2, which is not a complainant. But as you see the return loss, even though it's -5, there is at least a measurement in that operating frequency. And then look at this return loss. In the simulation is -19.569. When it comes to measurement is -18 and also -11, which is almost the same kind of criteria. And then next, the bandwidth. The higher the bandwidth or the larger the bandwidth, the better is the antenna. So the first when we see in simulation is 278.9. When we see in measurement is 360 and also 315. What can I conclude among this comparison? This shows that there are not much of differences between them. The criteria is almost the same. What can I conclude from this project? So first, the slots etched on the both side antenna resulted into frequency and lower frequency limit. This is actually can be explained from the measurement. Because remember, I have mentioned earlier that there are actually 4 operating frequencies where it started at 0.63 gigahertz. But due to the high VSWR and a very low return loss, which makes me not to add it in the report. But we can maybe make it to work better in lower frequency by making the antenna bigger or making more slots. Okay. And number 2, due to fabrication and measuring equipment limitations, other parameters of the antenna cannot be measured. This is because, for an example, I don't have the 3D results. I only have the polar plot, which is just about 2D. Now let me show the novelty. Novelty is actually, is there any event or is there any new kind of design that I did? So what are the new things is compared to my previous seniors report of both antenna, I have added slots. Slots were added, as you can see in the methodology this side on your left. You can see that the rectangular is actually named as the slots. And as you can see, there is no any transmission of feed line. Last but not least, commercialization. My project can be commercialized if by just adding a rectifier to design an antenna to work as a rectangle where it has a rectifier and antenna, but there's also involvement of impedance matching as well. And last but not least, to add ground plane to increase performance at antenna. As you can see in my current project, I didn't add any ground plane, but ground plane may give some changes, whether in the S parameter or in the frequency as well. Before I start showing on how I obtain the result, the rectangular inside the antenna is actually the slots. This is why it is called a slotted boat antenna. The middle here is the discrete port, and then the white color here is the substrate. Okay, now let me start simulation first. We have 2 kind of results, which is 1D result and also 2D result, including the far field. So in 1D result is the S parameter, where it's in 1.1151 gigahertz with -19.571 dB. And then we just have to measure line here to get their bandwidth, where it is at 28 megahertz. Okay, and then next is the VSWR. We just click on axis and then we choose what is the frequency, and then we will get the VSWR at 1.23. And then the 2D, 3D result is that this is for the E field, where I fix the phase at 90 and then I increase the density and I make it at perspective view and I can animate to see it. And this is the maximum 11,785 volt. And then next for the H field, The both of the E field and H field shows that the distribution is from the pot to the bow tie. That's what it meant. So the E field distribution and the H field distribution is the same. And then let's go into the surface current. Surface current, as we can see, there are more current in the front slots actually. There are 4 slots. In the front 3 slots has more current, which means more of it distributed from the pot because it's more nearer than the pot compared to the 4th slot. Okay, the final ending slot here. And then last but not least is the far field, where firstly I'm going to explain regarding the gain. This is in 3D form, where the gain is 1.699, and then the total efficiency and radiation efficiency is near to 0, which means very good. Same goes to the directivity. And then this is the polar. Polar, where these are the values, frequency, and then the main low magnitude direction is at 180 degrees, we can see here. And then the angular width, when it's at 3 dB, is at 82.9 degrees. Okay, first one is the printed version, where it uses a matte paper by printing it from a normal printer. Okay, it's a black and white ink because this is where we will transfer it to the PCB UV board by using the UV curing station. This printed version will be on the PCB UV board, and then we will insert inside the UV curing station for it to transfer the image to the board. And this is the ending of the look of the fabricated antenna. So as we can see, the middle wire, actually it's the soldering that wire, is actually for the SMA 5-pin female connector, because by using this female connector, we will connect to measure the radiation, measure the signal, S parameter, VSWR. So to measure the VSWR and S parameter, we use the network spectrum analyzer. So as you can see in S parameter S11, like I've mentioned in the poster presentation, I only chose 2. And actually the range of this is from 30 kilohertz to 9 gigahertz. As you can see, it's actually this antenna can work well in also higher frequency limits. And this is for the VSWR. And we can see the higher frequency limits has low VSWR, lower than 2. Next is to show the measurement of far field system. This is actually the RF chamber of FTKK, the research lab. This is actually when the transmitter and also the receiver, which is the slotted bow tie antenna, are in vertical version. Okay, and then how we measure is, it's to measure the receiver antenna. When it moves around 0 to 360 degrees, it has their own signal. So the signal and the data from the far field measurement system is plotted in Excel, which we get E field. So E field 1.215 is from 60 to 70, the negative 60 to 70, that's the signal. And for 2.25 gigahertz, the signal is from negative 13 up to 30.